Okay, I'll get started. Wanted to begin with a reminder that next Thursday, so just over a week from now, is Test 2. Test 2 will cover the material since Test 1. So it's the work we've done on magnetism, the work we're continuing to do on magnetism up until and including next Tuesday's lecture. So all that material between Test 1 and Test 2 is on Exam 2. It has exactly the same format, the same structure as Test 1, so that there are 3 problems where you want to show your full working out that are worth in total 80% of the test. They're meant to be good practice for them. It's meant to be the homework problems, the recitation worksheets, the problems I work through in class. Then there's 20% based on 10 true-false questions. Practice for that is maybe concept questions in the book or the concept quizzes that I give in lecture class. There is a practice test in the practice test directory. There is a practice test with the solutions and one without the solutions, and I think I have a video solution to the practice test. I just wanted to show you a list of the material. Here's the material for Test 2. So they say it's all that material since Test 1. Magnetic poles, magnetic attraction, repulsion, magnetic forces on current carrying wires, magnetic fields due to current carrying wires, and the work we're doing now on magnetic induction, which will continue in this class and will continue in next class and culminate next Tuesday. Any questions on all of that? Okay. Let me just introduce this material that we're going to cover in today's class. So, as of course you know, sunlight bathes the rotating Earth as the Earth orbits the Sun. That sunlight that's bathing the rotating Earth causes currents or flows in the atmosphere, causes currents and flows in the oceans. Over the last 200 years, roughly, we've learned how to harness or harvest that flow in the atmosphere and that flow in the oceans, to turn that motion, that flow in the atmosphere, that flow in the oceans, into electrical currents and electrical power. And we've learned how to deliver that electrical currents and electrical power to our homes. It makes our homes safe. It makes our lives healthy. It makes us comfortable. And it's only the past few generations, handful of generations, out of, I don't know, tens of thousands of human generations that have had this ability to harness and harvest the motion of the Earth's atmosphere, the motion of the oceans for electrical power and electrical distribution. How that's done is how that's performed is the basis of this class. How it's done, how it's performed is due to electrical generators that were discovered, developed by Michael Faraday and Joseph Henry, who we mentioned in the last class. Specifically in today's class, I want to talk about these 2 bullets here. We're going to talk about electrical generators that generate electrical currents, electromotive forces, electrical power from translational motion, from kind of here to there, translational motion. And then, second bullet here, we're going to talk about electrical generators that generate electrical currents and electrical power from rotational motion. And so that's the second bullet here. With the first approach to generating electrical currents through magnetic induction, we'll meet a new version of Faraday's law. It'll be this one here, and I'm going to talk about that. With the rotational case and the generation of electrical currents through Faraday's law, we're going to meet a second version of Faraday's law. It's this one here, and I'm going to talk about that. So today's class comes with two new equations that correspond to motional induction through translational motion, motional induction through rotational motion. Before I get on with this, let me just be clear about what we mean by electrical generators and how they relate to electrical motors. So this is the first time in this class we're meeting electrical generators. We actually introduced the idea of electrical motors a few classes ago. So electrical generators turn motion, they turn kinetic energy into electrical energy, the motion of electrons along a wire. So that's what an electrical generator is. It's something that transforms energy from one form to another form, from bulk motion, kinetic energy, into electrical currents, electrical energy in wires. Electrical motors are kind of the reverse of electrical generators, the opposite of electrical generators. If you remember when we talked about electrical motors, what they do is turn electrical currents, electrical energy, into kinetic energy, into motion. So when you're making a margarita at home, the blender, that's turning electrical energy, electrical currents into kinetic energy, the motion of the blades. The washing machine, the dryer, all these things involve electrical motors that are turning electrical energy into kinetic energy. Electrical generators are the reverse. They're turning kinetic energy, motion, some sort of motion, into electrical energy and electrical power and electrical currents. Okay, so let's start with the first topic. Remember, we've got two topics, one involving translational motion and generators, the other one involving rotational motion and generators. This is the setup that we're going to talk about. I actually have it at the front here, so I'm going to demonstrate it, but this is a picture of the setup. This is a very simple, unpractical electrical generator. This turns translational motion, kind of here to there translational motion, into electrical energy, into electrical power, into electrical currents through magnetic induction, through Faraday's induction. In this picture here, these are magnets. And so this region here is a region of magnetic field. And the magnetic field is kind of coming vertically upwards out of the magnets. So this is a region of magnetic field. In that region of magnetic field, I've placed an electrical circuit. It's a very simple electrical circuit. The circuit is made of these two rails. These are conducting rails, one upstairs, one downstairs. This movable rod. And then finally, you see the wires here, the red wire and the black wire, they connect to this current meter here. And so this makes a circuit through the current meter and the wires to the rail downstairs here, through the movable rod here, back through the top rail here, and back to the voltmeter or the current meter. And so we've made an electrical circuit. Through that electrical circuit is a magnetic flux, right? There's a magnet, and some of the magnetic field lines are passing through the circuit so that there's some flux through the circuit. Supposing I was to move the rod, move it left or right, I would change the amount of flux that passes through the circuit. I'd increase the flux through the circuit or decrease the flux through the circuit, depending which way I move the rod. If I change the amount of flux through the circuit, increase it or decrease it, what's going to happen according to law of induction, Faraday's law of induction? What's going to happen is there's going to be an induced EMF, there's going to be induced current. And so this is a way, if I move the rod, if I give the rod some movement, to turn that movement or motion into electrical currents, electrical potentials, electrical power. And so this is a simple generator. As I say, it's not a practical generator for generating electricity for our homes, but it is a simple generator for understanding how we might turn movement into electrical current. So let me just show you this. If you're at the back, you're going to probably need the binoculars that you brought or the telescope to see it. But here's the rails and the magnets, and here's the rod. Here I'm completing the circuit with this meter here. So this is going to show us the induced EMF or induced current in the circuit. Right now the big needle is pointing to 0. There is no induced EMF in the circuit, no induced current in the circuit. But if you watch the needle carefully, so it's going to be a small movement because not a very good generator, we'll see the needle move as I move the rod left and right. As I move the rod left to right, I'm changing the flux through the circuit, and changing flux, according to Faraday's law, is creating this induced EMF, this induced current. So let's try that out. Anybody see it? It's pretty tiny. It's tiny because combination of I'm incapable of moving this thing very fast, and also it's a small effect. But you see, when I move the rod left and right, we see that needle wiggling to and fro. I'm going to log that on Strava as my exercise for today. Okay. So that's a electrical generator. It's generating from motion of the rod a electrical current, an electrical potential, and electrical energy and electrical power. So let's see if we can understand the details of that setup. So here's a picture of it. I'm looking for the pointer, I've lost it. This is I'm calling this the helicopter view. You're imagining you're in a helicopter over the bench here and looking down at it. And if we look down at the arrangement, it kind of looks like this arrangement here. Horizontal bars here in gray are the rails. In brown here is the rod that I move to and fro. And over here, I'm completing the circuit. In this case, I've drawn the voltmeter or the current meter as a resistor here, but here's a complete circuit. So this is the setup. I wanted to introduce some quantities that are relevant to understanding this arrangement, and some of them are pictured on here. One is the length, the separation of the rail, so the length of the rod. Then there's the motion of the rod, that's down here, and then here's the force that I was applying to the rod to move it to and fro. We said qualitatively, based on our understanding, that if we move the rod, if you move that rod left or right, then you're going to change the number of field lines that pass through the circuit. If you change the number of field lines that pass through the circuit, you're changing the flux through the circuit. If you've got a time rate of change of flux through the circuit, you're going to get an induced EMF through the circuit. So we know that motion of the rod create an induced EMF. And this equation here, this right-hand side, is Faraday's law of induction that says that the rate of change of flux is the induced EMF applied to this particular arrangement, this particular geometry. And I'm just quoting this equation. You could derive this equation, but I'm just going to quote this equation and explain why it depends this way on the quantities on the right-hand side. So obviously it would depend on the magnetic field, right? If we have bigger magnets, if we could buy bigger magnets, we get a bigger induced EMF because we have a bigger change of flux. So it's in proportion to B. It's in proportion to the speed that I move the rod at. The faster I move the rod at, the faster I change the number of field lines through the circuit. And so the greater the EMF. So it makes sense that it depends on the speed. If I didn't move the rod, if V was 0, then I'd have no induced EMF. And if I could move it really fast, I get a large induced EMF. So it makes sense it depends on V. It also depends on L. If I made L bigger, supposing I doubled the separation between the rails and doubled the length of the rod. When I move the rod, I'd capture more field lines because I've got a larger area of circuit. And so the separation between the rails, or the length of the rod, also affects the induced EMF. The larger L, the greater the induced EMF. The smaller L, the lesser the induced EMF. So BLV is the induced EMF for this particular generator. It's an equation that describes this particular linear motion generator. If I wanted to picture the induced EMF as a function of time from this generator, it would be a graph that looks something like this. So time is horizontal, the induced EMF is vertical, and if I was to maintain the rod moving with constant velocity, I get a constant, and I couldn't do this, right? I wasn't able to do this. But if I could maintain that rod with constant velocity, supposing I had a big long string of magnets across here, and I could just walk that rod down there, then all the time I'm moving the rod, I'm getting an induced EMF. It would be this constant induced EMF here. So that's a rather simple arrangement that gives what we would call a direct current of induced current, a direct EMF. It's just a constant EMF. And that's going to be important when we look at the rotational motion case. Oh. I have no idea where I've gone. I've gone like 50 million slides. Let's look at an example, an illustration of this type of induced current due to this type of translational motion. So I'm going to work through this particular example here as an illustration of translational motion creating, in a magnetic field, creating an induced current. So let's just read through the question. In this question, I'm told that I've got a 35 centimeter long conducting rod. So again, this is the conducting rod. And I'm pushing that conducting rod at a constant speed. And that constant speed is 1.3 meters per second. So it's sort of everyday speed. And I'm pushing it across these rails through a perpendicular magnetic field that is uniform and has a strength of 0.3 Tesla. We've completed the circuit with a 9 ohm resistor here. So the combination of the resistor, the two rails, and the rod are an entire circuit. The entire circuit encloses some region of magnetic field, some field lines, some magnetic flux, and we're changing that magnetic flux by moving the rod. We're going to calculate several things here. We're going to calculate the induced current in that rod. And that's very interesting because we want to know, we're interested in the relationship between the motion that you're kind of putting into the generator. That's the speed V. And the induced current, that's what you're getting out of the generator, the electrical current. So we're going to start by looking at that relationship between the speed in and the current out, like the kinetic energy in and the electrical energy out. The second part of the question says, what's the applied force that you need to keep the rod moving at a constant velocity? What force do we need to apply to keep the rod going at a constant velocity? You might think, well, if it's going at a constant velocity, actually, why do I need any force whatsoever? Things will move at constant velocity if there's no net force acting on them. So at first sight, it might look like we don't need any force whatsoever to move the rod at constant velocity, but we're going to see that it's a little bit subtle and you do need to apply a force, and we're going to work that force out. So that's the second part of the problem, and it really is a detail about understanding how this generator will work. The third part of the problem comes back to our use. Why do we use generators? We use generators to turn energy of motion into electrical energy, and we're going to find out how much energy of motion, power, we put into this arrangement. We're going to compute that, and we're going to compare it with how much energy, electrical energy, we get out of this arrangement. Again, this is a key to understanding its operation as an electrical generator. So this is a big, I've got several parts to this problem. It's a big exploration in numbers and ideas about how this generator is going to work. So I'll do this on the document camera. Here we are. I started it off with a sketch. Again, it's this helicopter view of the problem. I'm looking down on the magnets, and I'm looking down on the circuit that's immersed in the magnets. And I've annotated it with the various quantities I'm told in the problem. So the rod has a length of 0.35 meters. It was 35 centimeters. The rod has a speed 1.3 meters per second. The rod is immersed in this, and the circuit is immersed in this perpendicular magnetic field that's coming out of the screen towards you, going into the screen, away from you, and it's 0.3 Teslas. And finally, the resistor that completes the circuit is 9 ohms. So the first question was, what is the induced current in the circuit? So what's the induced current in the circuit? I'm going to use two laws of nature to figure out that induced current. One is, I'm going to actually use Ohm's law for the relationship between the current and the voltage in a resistor. And then the second one, for us, the new one, is I'm going to use Faraday's law. Faraday's law, as applied to the linear generator, that the induced EMF, that voltage that's induced is equal to BLV. And so I'm going to combine those two laws. So let me start that going. The voltage across the resistor, the induced EMF across the resistor, is what determines the current that flows in the resistor and around the circuit, and that current is determined by Ohm's law. So here I just plugged in Ohm's law. V equals IR, or here it's epsilon, the induced voltage, equals IR. Faraday's law says that induced EMF is produced by a changing flux. And in this case, the change in flux is given by BLV. The magnetic field that's passing through the circuit, the length of the rod, and the speed of the rod. that determines the induced EMF. Basically, what we're doing is changing the flux by changing the shape of the circuit. And the speed of the rod determines how fast we change the shape of the circuit, but also the length of the rod is determining how fast we change the circuit. And the amount by which we change the area of the circuit multiplied by the magnetic field that's bathing the circuit gives us the rate of change of flux. And so that's what we've written down here. So I'm using that equation I introduced on the last slide. All I've got to do now, if I want the induced current, is just rearrange this. It's just going to be BLV divided by R. And so I've just got to feed in all the numbers. Because they're small numbers, I'll actually try writing them out. I don't like writing out powers of 10 on the document camera. It's 0.3 Teslas. We've got 0.35 meters for the length. We've got 1.3 meters per second for the speed. And we've got a resistance that was 9 ohms. And if we multiply all those things together, we get a current. That current is 15 milliamps. I think I got 15.2 milliamps, but 15 milliamps. And that's the generator, right? We put in some speed, V, 1.3 meters per second. That's translational motion. We got out, what did we get out? We got some current out. We got out 15 milliamps. If I had put in twice the speed, supposing I put in 2.6 meters per second of speed, I would have got out twice the current. I would have got 30 milliamps out. If I put in half the speed, whatever that number is, I would have got half the current out. So that's the relationship between the speed in, the translational motion in, and the electrical current out. Okay, after all that, I forgot what the second question was. Oh, it was about the force. The question asks, what force do you have to apply to the rod to move it left to right in this magnetic field? So the first thing is, why do you have to apply any force whatsoever? Why would we have to apply any force whatsoever? The reason we have to apply a force is we've got a current that's flowing in this circuit. We've got an induced current that's flowing in this circuit. That induced current in the rod is going to experience a magnetic force. That magnetic force actually will try and slow down the rod. It will try and stop the rod. And so we have to overcome the magnetic force on the induced current to keep the rod moving. So that's the basic reason we've got to apply a force, is that there is another force, a magnetic force, that appears when the rod is carrying a current, and we have to overcome that magnetic force. Let's start by trying to figure out I want to figure out the direction of the force that I have to apply. That means I've got to figure out the direction of the magnetic force that I've got to overcome, counteract, which means I've got to know where that magnetic force is coming from the electrical current, which means I've got to know the direction of the electrical current in the loop, in the circuit here. So I'm going to start by figuring out the direction of the current in the circuit. That's going to enable me to figure out the direction of the magnetic force on the rod, which is going to enable me to figure out the direction of the force that I apply to the rod. So let's start by trying to figure out the direction of the current that flows in this circuit. Right now we just know that 15 milliamps flows in the circuit, but right now we don't know whether it's going clockwise or counterclockwise around this circuit. But this is a type of problem we've solved already. To figure out whether it goes clockwise or counterclockwise, we use a combination of Lenz's law and the right-hand rule. So Lenz's law says that the induced magnetic field of the induced current will oppose the change in the external magnetic field. So if we look at the sketch, as the rod moves towards the right, the number of field lines through the circuit into the screen is getting bigger and bigger. So there's more and more field lines through the circuit as we move the rod towards the right. That means that the induced current wants to make a magnetic field, counteracting that change, wants to make a current that's out of the screen. So it wants to make a magnetic field that's out of the screen. So the induced magnetic field is out of the screen because the external field through the circuit is into the screen. So we want an induced field out of the screen. That, if we use the right-hand rule for a circular loop, tells that and I'm using the right-hand rule for a circular loop, which describes the relationship between the current direction and the field direction. If the induced field is going to be out of the screen, then the current must flow counterclockwise around the loop. And so that's an important step that I just made there. Let me mark it on here. B induced, I'll call it B induced here, that's out of the screen. And this electrical current for that direction of the induced field, the induced current for that direction in the induced field must be counterclockwise. So it flows from the top to the bottom through the resistor and is flowing this direction, bottom to top, through the rod. And so that's just a little bit I've added to the diagram where we know the direction of the current now. Well, we've now got a current on the rod, through the rod, that's bathed in, immersed in a magnetic field. And in general, if you've got a current in a magnetic field, you're going to get a magnetic force. So let's figure out the direction of the force on the electrical current. The current is up. So I'm going to use a right-hand rule again. It's the one that relates the direction of the current, the direction of the magnetic field, and the direction of the force. I'm going to point the palm of my hand up for the electrical current. I'm going to curl my fingers in the direction of the field, that's into the screen. My thumb is now pointing over towards the right. That's the direction of the magnetic force. It's towards the right. And so, given this current in this magnetic field, we know we've got, I'm going to draw the force arrows up here. We know we've got a magnetic force that's over towards the left-hand side. And so there's a magnetic force on that rod because it's a current-carrying rod in a magnetic field. If we didn't exert a force, that magnetic force would slow and stop the rod. It wouldn't continue to move. We have to exert a force to keep that rod moving at constant velocity. We have to exert an equal and opposite force so that there's no net force to keep that rod moving at constant velocity. So the applied force has the same size but is in the opposite direction, over towards the right. Okay, that was a lot of arguments to get to the point that we do need to apply a force because we do have a magnetic force that's breaking the rod, slowing down the rod, and we had to work out what direction that magnetic force was in, and we had to use right-hand rules and Lenz's laws, and then we could, once we got the direction of the magnetic force, use the fact that the net force must be zero to figure out the direction of the applied force. So I went through a whole chain of arguments to get to that point. So it's quite a complicated, quite a sophisticated chain of arguments to get to that point. But when we stand back now and look at the situation, we realize that there are two forces that are acting on that rod. There's a magnetic force that's trying to slow it down, and there's my force that's trying to keep it moving at constant velocity. If I can figure out the magnetic force, that strength, that determines the strength of my applied force. And so that's the key idea here. So in part 2, I think I wanted, what did I do? I changed something. Crap. Okay. We want the applied force. The way we're going to figure out the applied force is it's equal to, in size, now I'm worrying about the size, is equal to the magnetic force. And the magnetic force on a rod, current carrying rod, is BL times the current in the rod times the sine of the angle between the current direction and the magnetic field direction. So this is an equation we met before. We know the magnetic field. We know the length of the rod. We know the current, induced current in the rod. We know that the magnetic field direction and the current direction are at right angles to one another. In this picture here, the current is up and the magnetic field is into the screen. So 90 degrees, so sine theta is 1. And so here all I've got to do is feed in the field, 0.3 Teslas, the length of the rod, 35 centimeters, 0.35 meters. The current that we figured out that was flowing in the rod is 0.015 amps. And multiply those together. I've written it down somewhere, I hope. And I got 1.6 times 10 to the minus 3 newtons. 1.6 millinewtons, 10 to the minus 3 newtons. And so that's the force on the rod. Look, calculating the force was not the hard part of that problem. Arguing why you need a force and what is the direction of the force and how it's related to the magnetic force, that was the harder part of that problem. So that's the applied force. Everybody okay with that? No. Third part of the problem. Third part of the problem, if we can possibly remember it, it was what is the power that's being supplied to the generator, and what is the power that's being dissipated, delivered by the generator. So the kind of the power in and the power out. How on earth are we going to figure the power in and the power out? Well, think of what we are putting in. What we're putting in is a force. We're exerting a force over some distance. So the energy that we put in is force times distance. The power that we put in is force times velocity. So to figure the power in, I'll just put P subscript in for power in. All we've got to do is actually, I mean, you may well not remember this, but the power delivered by a force in moving an object is the product of the force times the velocity, the speed, the motion. Just like the work done by a force is the product of force times distance, the power supplied by the force is force times velocity. So we're just going to use this equation from Physics 211. That's the power in, and we'll go ahead and calculate that. What about the power out of the electrical generator? How are we going to calculate the power out of the electrical generator? Well, we can, because that power actually subsequently gets dissipated in the resistor. It warms up the resistor as the current flows through the resistor, and we have an equation for the power dissipated in the resistor. So the power out, I'm going to just use the fact that the power dissipated in the resistor, which is where the electrical power is ultimately going, is I squared R. The current squared times the resistance of the resistor. So we've actually, when we think about it, we've got an equation for the power that we're putting in through the force and the power that we're getting out through the current flowing through the resistor, through the heating up of the resistor. So I can plug in the numbers for these. I know the force is 1.6 times 10 to the minus 3 newtons. I know the velocity was, that was 1.3 meters per second. If I multiply those two things together, I hope I wrote this down too, 2.0 milliwatts. 2.0 times 10 to the minus 3 watts. So that's the power in, just based on the force and the motion. And the power out, I wrote this wrong, is I squared R. The current, we figured that out, is 15 milliamps, so 0.015 amps. We've got to square that. Multiply it by the resistance of the resistor. That was 9 ohms up here. 0.015 squared times 9, if you work this out, this is a bit of a miracle here, is also 2 milliwatts. And that's the same just because of energy conservation. So we're putting in some power. You know, I'm applying some power. I'm putting in some energy. That's the work that I do. We're getting out some power. We're getting out some energy. That's the work done in the resistor by the current. No energy is lost, or no energy is gained or destroyed. We're just transforming energy from one form to another. We put in 2 milliwatts. We're getting out 2 milliwatts. And so that's kind of the big picture of the electrical generator. It turns one type of energy or power into another type of energy or power. It turns the motion of the atmosphere or the oceans into electrical energy, electrical power. Okay. Second topic. Second topic was the electrical generator involving rotational motion rather than translational motion. So it's another way of turning movement into induced currents, induced EMFs, but it is rotational motion rather than translational motion. This is a more practical electrical generator. The previous case was a less practical electrical generator. Let me show you a demonstration of that. Firstly, let me show you this picture. So this is a picture of a simple generator using rotational motion, and I have this generator here. It has a loop of wire here. In fact, it has hundreds or maybe thousands of turns of wire here. So what looks like just a copper sheet is actually hundreds or thousands of turns of copper wire wound around some frame here. Those loops of copper wire are immersed in a magnetic field. The magnetic field is due to this magnet here with north and south poles. The magnetic field in the location of the loop of wire, or many loops of wire, streams from left to right, or right to left. So this is a loop of wire in a magnetic field. So supposing I rotate that loop of wire in the magnetic field. If I rotate the loop of wire in the magnetic field, I will change the flux, the magnetic flux through the loop of wire. Just like when I moved the rod across the rails, I changed the flux through the circuit made by the rod. Here, if I rotate the coil, the loop of wire, I'm going to change the flux through that loop of wire. And so that's going to induce an EMF, it's going to induce a current, it's going to create electrical energy, create electrical power. So this is a generator. If I rotate the loop of wire, if I put in to the generator motion, rotational motion, kinetic energy, I'll get out from the generator electrical voltage, electrical current, electrical energy and power. So this is how the generator will work. Let me show you. Here is the generator. Magnetic field runs horizontally in the room. I'm sorry, it's so tiny. Here's the loop of wire, the many loops of wire. And I can rotate this. Now in this case, I've connected the leads of the loops of wire that are in the magnetic field. They're connected to these two wires, the red wire and the black wire, and they're also connected to a meter that's going to tell us the current or the voltage. So exactly like this arrangement over here. So watch the needle this time. We see it's vertically upwards right now because I'm not touching anything. But then I'm going to rotate the loop of wire. I'll rotate it clockwise and counterclockwise, kind of like I moved the rod left and right. And so I'm just going to rotate it, and we're going to watch the needle. And now we've got a big deflection compared to the linear motor. Much easier to turn rotational motion into electrical energy than it was to turn our translational motion into electrical energy. So this is a second generator based on rotational motion. This is so easy I'm not even going to log it in Strava as an exercise. Well, I actually will, but okay, here's a little sketch of that arrangement. It's kind of a simplified sketch of that arrangement. It has all the key components in it. So in the sketch here, I've got a region of magnetic field. There's a north pole of a magnet here upstairs. There's a south pole of a magnet downstairs here. Between the two poles is a magnetic field emerging from the North Pole and heading towards the South Pole. So this is a region of magnetic field. In that magnetic field, I've got a loop of wire. Now this might be a loop of wire, might be 10 or 100 or 1,000 loops of wire. So there's a loop of wire in here. If I rotate this loop of wire in that magnetic field, what's going to happen? The flux through the loop of wire is going to change. If the loop of wire here was standing vertically between these two poles, then there would be a lot of field lines passing through the loop of wire. If the loop of wire here was laying horizontally between the two poles, then there'd be no flux, magnetic flux through the loop of wire. The field lines would just pass over the top or underneath the loop of wire. So if I was to rotate this loop of wire, turn the loop of wire, then I would be changing the flux through the loop of wire, and as we now know, we would get an induced EMF, an induced current. We would have created a generator, electrical generator, based on rotational motion. So that's the basic idea here. There's a lot of details about how you get the electrical current, the electrical voltage out of this arrangement. I won't go into those details here. This is the sort of arrangement that you use. We're lighting a lamp here with the induced current, with the induced EMF, due to the changing flux in the loop of wire. Okay. Just like you could write down a dedicated version of Faraday's law for the induced EMF in the linear electric generator, you can write down a dedicated version of the induced EMF in this rotational motion generator. So that just like the previous case, there's a special equation, BLV, that told us the induced EMF there. There's a special equation here, it's NBA omega sine omega t, that tells us the induced EMF here. And just like the last case, I'm not going to show you, I'm not going to derive this. We don't want to derive this. We didn't derive the last equation. We didn't want to derive it. But we wanted to look at it and understand how it works. So here's the induced EMF created by the rotational motion generator. And let me just walk through the various ingredients in here. The first obvious one is to create a change in magnetic flux, we've got to have a magnetic field. So that there's the magnetic field, the B is in the equation. And so obviously the larger the magnetic field between the poles, the greater the induced EMF. The smaller the magnetic field, the smaller the induced EMF. Then there's a couple of quantities, A and N, that reflect the characteristics, the properties of the loop of wire that you've immersed in that magnetic field. So A, uppercase A, is the cross-sectional area of the loop of wire. The bigger the cross-sectional area, the more field lines you'll capture in your loop. And the faster the rate of field line change or flux change as you rotate the loop. Just like the greater the distance between the rails, the more field line we captured in the linear generator, which meant a greater induced EMF, a greater induced current. And so this A here is the cross-sectional area of this loop, and the bigger it is, the more induced EMF you get, the more induced current you get. N is just the number of turns of loop you have. If you had 10 turns of the loop, it's really just like having 10 loops chained together in that magnetic field. You'll get 10 times as much induced EMF because each loop gives you a contribution to the induced EMF, so you'll get 10 times as much. If you had 1,000 turns, it's like having 1,000 loops immersed in the magnetic field, so you'll get 1,000 times as much induced EMF. So that's the N here. So we've done the B, we've done the, which is the external field that we bathe the arrangement in. We've done the N and A, which are the loop properties. What about the omega sine omega t? Omega is the angular velocity, not the linear velocity, of describing the motion of the loop. So the key ingredient in the linear generator was that we would move the rod with some velocity v. Without v, we don't generate anything. In this case, the key ingredient is that we're rotating the loop of wire. That's the omega, the angular velocity, or the radians per second. The faster we turn it, like the greater the speed, the greater the angular speed, the greater the induced EMF. So that's the omega here. But in addition, there's this sine omega t. So that is a difference, and that arises because the rate at which the flux changes through the loop of wire actually varies as you rotate the loop. Sometimes it's changing fast, sometimes it's barely changing at all as you rotate the loop in the magnetic field. And the rate of change of the flux is described by this sinusoidal function. So that's the full equation. You'll see that in more detail soon, I think. Here's just a kind of illustration that would be the case. Actually, it's not a great illustration. Let me try this in words. Supposing that the magnetic field is streaming from the left of the room over to the right of the room, from left to right. That's the direction of the magnetic field line. So imagine all these field lines pointing over here. And then I have a loop, a rectangular loop immersed in that magnetic field. If the loop is horizontal, right, at that moment there's no flux through the loop. But a tiny change in the loop, supposing I tip it a little bit towards the left, right, or I tip it a little bit towards the left, that creates a change that's a change in flux. There's actually a big change in flux if I move the loop that was horizontal a little bit over here clockwise or a little bit here counterclockwise. So these are big changes in flux. If the loop is standing vertically, it's collecting a lot of flux. There's a lot of field lines going through the loop. But if I change its angle just a little bit away from the horizontal, I tip it a little bit towards the right or a little bit towards the left, it barely changes the flux through the loop. The flux hardly changes. So this geometry in the magnetic field, although there is no flux through this loop when it's horizontal, if we rotate the loop, there's a big change in the flux. This geometry, although there's maximum flux through the loop, if I rotate the loop a little bit, there's barely any change in the flux. And it's not the size of the flux that counts in generating the induced EMF. So it's not the fact that there's zero flux here, maximum flux here. It's what counts is how fast the flux changes. The flux changes really fast here, you're going to get an induced EMF. The flux changes barely at all here, you're going to get a very small induced EMF. So that's a key thing. And that's the beauty of sine omega t. It accounts for all of that for you. Sine omega t has peaks, a peak and a trough, right? And those peaks and trough correspond to this geometry here, where you're going to create a large induced EMF. Sine omega t has nodes where it's zero. That corresponds to this geometry here, where the induced EMF, if I tip the coil a little bit, will be zero. And so that's the story of the sine omega t. Here is a picture of the equation, a graph of the equation, and especially of sine omega t. If you look at the graph on the left-hand side, this is the electromotive, the induced EMF from the generator involving rotational motion. And unlike the translational motion generator, suppose there we imagined moving the rod at constant velocity, we got a constant voltage out, a constant induced current out. If you rotate the loop at constant angular velocity, you don't get a constant voltage out, induced EMF out, or induced current out. You get a sinusoidally varying induced EMF, induced current out. The maximum induced EMF is NBA omega. That's where sine omega t is 1. But there are moments when the flux isn't changing and the induced EMF is 0. You can see them here where the curve crosses the horizontal axis. And so the rotational motion generator compared to the horizontal motion generator, it's different in a number of ways. It's much easier to generate electrical voltage, electrical currents with the rotational generator than it was to generate currents and voltage with the translational generator. But also the nature of the electrical currents and electrical voltages is very different. Here you get what we call an alternating current, voltage out of the rotational motion generator if you turn the loop or wire at constant angular velocity. In the translational case, you got out a DC, direct current, DC voltage out of the generator when you move the rod with constant velocity. So that's a big difference. Okay, quiz question. Let me publish this. And I'll give you a couple of minutes to think about it. In this problem, there is pictured 3 geometries of the loop of wire in a magnetic field. And the question is, which of those 3 geometries creates the largest induced EMF as the loop of wire rotates? I feel I want to make sure we all understand what I'm picturing here. The loop of wire is into the screen or out of the screen in all these pictures. So it's kind of a side view of the loop of wire. This grey bar, dark grey bar, is the front side of the loop of wire. The little circles above and below are the currents heading into the screen and out of the screen. So the three geometries are magnetic field streaming towards the right, the loop of wire standing vertically, the loop of wire lying horizontally, and the loop of wire being at some intermediate, in-between angle between vertical and horizontal. Okay, I'll get started. This question can be a little bit of a trap. The trap is that this orientation vertically has the most flux, magnetic flux through it. There's field lines, lots of field lines passing through this arrangement. But actually this arrangement is creating zero, or approximately zero, electromotive induced voltage and induced current, because what counts is the change in flux. As I rotate about that location, I barely change the flux. So it's not this arrangement. This arrangement, on the other hand, well, you might think, well, this has no flux through it. And it does have, if the loop is horizontal, there is no flux through this. But a little change, tipping the loop towards the left or towards the right, creates a big change in flux, a big change in the number of field lines through this loop. And so this arrangement is generating the maximum electromotive force because the rate of change of the flux is biggest. The third geometry, C, is just somewhere in between. It's in between the maximum of the electromotive forces and the minimum of the electromotive forces, because the flux there is changing, but not as much as it changes in this geometry. Okay, I'm going to end on a numerical example for the rotational motion of the rotational generator. In this particular problem, if we just read through it, I've got a loop of wire. We're told its area, 0.1 meters squared. We're told the number of turns, 1,000 turns. And we're told the resistance of the loop of wire, 12 ohms. And we're told that we're rotating that loop 60 turns, 60 complete revolutions per second in a magnetic field that's 0.2 Teslas. So that's all the information just given in that one sentence there. Then we're asked to figure out a number of things. That loop of wire, or that coil, as it rotates, has a change in flux through it, so it's going to have an induced EMF, an induced current. As we've been discussing, we're going to calculate that induced EMF, that induced current, by Faraday's law. So that's the first thing. We're going to be applying that special version of Faraday's law for a rotational electrical generator, the NBA omega sine omega t. So that's the first step. Second part of the question says, what applied torque? You know, I turn the the coil in the demonstration with a little torque. What applied torque do you need to keep the loop of wire turning with constant angular velocity? You might think, why do I even need a torque? Like before we thought, why do I even need a force? Well, you do need a torque because you have to oppose a magnetic torque that's trying to slow down the rotating coil, just like we needed a force to apply a force because of the magnetic force that was trying to slow down the rod in the previous example. So we do need a torque, like we do need a force. We're going to figure that torque out in a similar way that we figured the force out. Finally, we're going to compute, since this is an electrical generator, what electrical power what power we're putting in by rotating the coil, and what electrical power we're getting out through the electrical circuit. Okay, I'm going to challenge myself to work on the document camera. It doesn't want to accept that challenge somehow. Okay, now it's on my side. I made a little sketch of the arrangement. Left to right, the magnetic field lines. The coil is described by this sort of angled line with the two little circles at the top and bottom. Remember, this is my side view of a coil. I don't really know how to draw the coil in 3 dimensions, but if we look from the side, we see the side that's nearest us, and we can imagine the current flowing in or out at the top and in and out or at the bottom. I've added a little arrow to show the rotation, the rotational motion of the coil in the magnetic field. And I've annotated the sketch with all the numbers. We were told the magnetic field is 0.2 Teslas. We're told that the rotational motion was at 60 complete revolutions per second. I've converted that by multiplying by 2 pi to the angular velocity. The angular velocity is 2 pi times the frequency, the number of revolutions per second. So it's actually, the angular velocity is 377 radians per second, because there's 2 pi radians in one complete circle. I also wrote down the characteristics of the coil that we were told. So we were told the area of the coil, we were told the number of turns of the coil, we were told the resistance of the coil. First thing was to figure out the induced EMF and the induced current. Actually, the question said, what's the max? What's the maximum induced EMF and induced current? So let's figure those things out first. This is part 1. We want maximum, that's the subscript here, induced EMF. Maximum induced current. The M is the subscript for maximum. Okay, so what are these guys? Let's see if I can do this. Maximum induced EMF, that's given by Faraday's law, rate of change of flux. Faraday's law applied to the electrical generator involving the rotational motion is NBA omega sine omega t, but we're interested in the maximum induced EMF, so it's just NBA omega. That's when sine omega t is maximum, it's when it's 1. Okay, so this is actually straightforward application of this equation, filling in all the numbers. We've got 1,000 turns, we've got a 0.2 Tesla field. My watch is telling me I'm running out of time, thank you. The area is 0.1 square meter. And finally, the angular velocity is 377 radians per second. Multiply all those things together and you get a voltage, that's the induced voltage, that's generated by the rotating loop in the magnetic field. It comes out to be 7.5 kilovolts. So it's a large voltage, yes.
Did you say why we didn't multiply by sine omega t?
I didn't do that because that's a good question. Let's make sure we're all getting that. I'm figuring out the maximum induced EMF. And so the maximum induced EMF is when that sine omega t is 1. And so that's why I didn't do that. But if we wanted it at any other moment or instant, we could put in the time, plug it into sine omega t, and then you would get the voltage at that moment. So there's a good reminder. What about the current, the induced current? Well, that's easy with Ohm's law, like we met before. If we know the induced EMF across the coil, we can figure out the current through the coil, knowing the resistance of the coil, knowing Ohm's law. So the induced current is the induced EMF divided by the resistance of the coil. So this is 7.5 kilovolts divided by the resistance of the coil, which was 12 ohms. If you calculate that, that's 625 amps. That's a lot of current too. So again, a very effective way of generating electricity, because you can rotate things really fast and you can make lots of loops of wire that rotate in that magnetic field. And so it's a very effective way of generating electricity, electrical energy, electrical power. And that's how it's done in reality at a power station or whatever. Second part of the question was, what is the applied, this is a tau if you're wondering, what is the applied torque that you need to maintain the circular motion? So what is the applied torque that we need there? We need an applied torque because we have a magnetic torque that's being exerted on the current carrying loop in the magnetic field that's trying to slow down the current carrying loop. So the basic idea here is that the applied torque is going to be equal in size, so I'm thinking about the size of the torques here, to the magnetic torque that is experienced by the coil as it rotates through the magnetic field. Yes?
Your screen froze.
Oh yeah. That's not good, because I have no idea how to fix that. Oh, there's a button called freeze. That's interesting. Thank you. That's a very, I don't know why I would want to freeze, but anyway, we need a. I'm really running out of time here. We need a applied torque because we got a magnetic torque, and we got to overcome that. And way back a few classes, we figured out what the magnetic torque was of a loop of wire in a magnetic field. It was the magnetic moment mu times the magnetic field times sine theta, but we want to know the maximum torque and the applied torque and the maximum magnetic torque. And so it's just mu b. It's just the magnetic moment of the loop of wire times the field that it's immersed in. That's the torque that we've got to overcome. Magnetic moment just is a reflection of the properties of the current carrying loop of wire. It's the number of turns times the area times the current that's flowing. We've got to multiply the field by that. And if you do that, because I'm running out of time, my watch is still telling me, I won't plug in the numbers, but it comes out to be, if you do plug in the numbers, where is it? 12.5 kilonewtons meters. So that's the torque. The final question, I want to at least write it down for you, is what power are you putting in and what power are you getting out from this electrical generator? We found the power in the previous example that went into the generator by multiplying force times velocity. It's the same thing here to find the power in